Oh, guys. So we did yesterday. I gave you some limits, which are very important. Hopefully, you understand them, because if you understand them and literally only one theorem that I'm going to show, which is very intuitive and works very fast, you can technically solve any limits if you're good with computation. Now, that's a big F. But I apparently have to show you what continuity is, although realistically in this course, I don't think you're ever going to prove that, but I have to show you. I didn't need to do that. But unfortunately, continuity requires the definition of a limit. So, and I haven't done that. I haven't defined what a limit is thoroughly. So today is going to be a combination of actually some exercises and some theorems, or complicated definitions, which I'm going to translate them to English for you guys. Okay. So, let's just start with what a limit is. What is a limit? Okay. The formal definition sounds like this. I can say that limit when x goes to a of f of x is equal to big A. This is basically saying that whatever epsilon greater than 0, there is a delta greater than 0, such that, and again, I will translate this, I promise. Okay. For all okay, this is the formal definition. If you're more tech savvy, I did my job. This is the formal definition of the limit. Now, English translation sounds like this. So this is, the formal English translation is, and I'll actually draw the English translation. So when I'm saying that a limit of an f of x when x goes to a is big A, I'm basically saying that I can make the difference f of x minus a. This is just absolute value. So if it's minus 0.2, it's just 0.2. I'm just talking about the absolute value of the difference, okay? I can make this difference as small as I want for sufficiently close enough x to a. Okay, this is basically the definition. Now let me actually draw it for you guys. Okay, so here's the idea. Let's just draw it in like one dimensional so it doesn't get complicated. Okay, this is big A, and let's just say I'm taking f. I want to show that limit of f of x when x goes to a is a. Okay. Now, when I'm saying that this limit goes to a, I'm basically saying that if I choose x as being a minus 0.1, okay, I'm getting close to a minus 0.01, I'm getting closer to a. Careful, I don't have to go at this point. I'm not saying I'm going close from any direction, so I can go closer here. Okay. Basically, the closer I move my x to a, the closer this is. This is f of a minus 0.1. This is f of a minus 0.01. Basically, the closer I move x to small a, the closer big f of x goes to big A. That is the, I guess, formal definition in English. And then they're basically saying, okay, after some point, if I just choose x close enough to a, if it's just close enough to a and some parameters, it is only going to get functions in this small interval around a. And the idea is that you make that interval smaller and smaller and smaller until you just get to a. Okay, so that's the idea. You just get, I think I even got some colors. if this is A, the idea is that you start with this big interval, and then you make it smaller, 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 until you're basically stuck with A. That is the whole idea of a limit, okay? Now, are you actually going to use this definition of the limit, the formal or the, I guess, informal definition of the limit? Probably not. But, you know, if you're going to use limit from now on for the next couple of weeks, it's probably better to know what it is or understand it. Okay? Now, we're going to do a lot of examples on limits and whatever, but let's get the definitions, I guess, part out of the way. Yeah. Yeah. Sorry about that. So it's basically whatever epsilon, so whatever interval you want me to be close to A, I can find another interval such that I make X close to the small a, all the values are going to be inside the interval of the function. That's kind of the idea. Maybe this A notation isn't the best because it gets confusing. Let's just say, I mean, I could just put it B and repeat it with B, like this. So if you want me to make f of x close to A up to some parameter, I can come up with a parameter in which I make X close to B, and then I did what you wanted me to do. That's kind of the idea. Now, it's kind of weird that you've used continuity and had theorems about continuous functions, but you never actually were taught what continuous is. So it's kind of backward, but let's just do continuity. Okay, so I'm basically going to say a function is continuous at x equals A if limit when x goes to A of f of x is equal to f of A. Okay, and after you've written this, let me just show you what it basically means. It just stops the counter example that I'm going to show you. Usually, I don't know if you were even taught continuous, but when I was little, I guess we were taught continuity as basically just not lifting your pen up. Okay, so basically, this is my A. I don't know, some f of A here. This is my B, some f of B here. And we were taught, okay, it's continuous if I just unite these points without lifting the pen. That was the definition of continuity. It just keeps on going. It's continuous. Sorry? Oh, sorry about it. Yeah. Okay. Basically, you're just linking 2 points without lifting the pen up. Okay. This limit, this definition, basically just stops the case where you have something like. Let's do another drawing. You just stop the case where you have. So again, I'll just draw a similar picture. A, B, f of B. I think I put f of A somewhere here. Okay. It basically stops, and let's say we have a C here, f of C. Okay. That limit thing basically says that when I reach this point f of C, this f of C point is just not randomly somewhere here. Okay, because there are functions that just go like this. Here they stop, the point C is here, and then they continue like this. And I can basically give you a function that's not continuous, that's continuous in an infinite amount of points and incontinuous in an infinite amount of points. So functions get very, very weird. Luckily for you in this class, that's not going to happen. Okay, you're going to get nice functions. So with a discontinuity, which I'm going to define at one point. But basically, it's just saying that if the function goes like this, we can't just randomly jump up. That's all the limit. That's all that the limit says. And if that happens, you'll have a continuous function. Okay. Now, obviously, if this doesn't happen, then you have a discontinuity. If not true, function has discontinuity, or simpler, not continuous at A. Okay? So for example, this function would not be continuous at C because the point is actually somewhere here, I assume. Okay, now properties. Again, unless you are required in this course to show continuity, unless the problem specifically asks you show that the problem is continuous at some point, you can assume it's continuous. Like even I think through all your regular problems and homework, you automatically, when you had the extreme value theorem, I told you to just write f is continuous. Okay, so you don't have to prove this unless the problem specifically says prove that it's continuous. When you're using extreme value theorem, just write closed bounded continuous. I'm done. Okay, you don't have to prove it in that case. But I think especially in the just some seminars, I don't know if it's really in the mandatory assignments, but some seminars you will have to just prove continuity for fun, which in the end are just limits. Okay. Now, let's give a particular example of a function that's not continuous. Let's just take f of x is equal to 1 x minus 1. Right, I just took this function. What's the problem here? Well, the elephant in the room is the fact that x can't be 1. Okay, if it was 1 over 0, question mark, does not exist. Furthermore, we have that if x greater than 1, f of x is greater than 0. If x smaller than 1, f of x smaller than 0. And I guess two approaches right now, especially when you're in neural limits, you just try to see what's happening there. You can just you can just take close values to 0 or to 1. So for example, I can't put 1 here, but I can put 1.01. I can put 1.001 inside. Okay, so I can just see what's happening. But this particular case just allows us to introduce another term, because let's just say I wanted to compute limit of x going to 1, f of x. Okay, I'm kind of having a lot of troubles right here. Okay, why? Because especially since when you're first dealing with limits, this is kind of hard. I have some function that's negative, I have a function that's positive, depending which side of 1 I'm looking at. So what am I doing? Am I just using the negative and the positive? Am I comparing it? And plus, this f of 1 is not even defined. So apparently my definition is terrible and doesn't work. Okay. So what do we do in this case? In this case, the first observation would be that it's not continuous, right? F of 1 is not defined. There's a huge jump there. So that's my intuition. If we weren't even to graph it or plug it into the Wolfram alpha, I don't know what you use nowadays, but it would just be, this is my 1. And I haven't really graphed it before, but I would think that the function just goes like something like this, and then something like this. Hopefully, something like this. I meant. Hopefully, I'm drawing is too big for fix it. Okay, so I think this is the function right now. Okay, now does this look like a continuous function to you guys? This is 1, by the way. Well, it doesn't really look that nice. It doesn't look like something that I drew right here. It doesn't look that continuous. And this is where you have a discontinuity here at 1. Okay, because this is 1, this is where it's supposed to be, and the other part says this is where it's supposed to be. So it's actually completely terrible. Okay, but when you draw this, you're going to tell me I need to take the limit from the left and the limit from the right. Because obviously this limit over here, you know, the values that are here are completely different than the values that are here. Do you guys agree with that? Like this is going towards a plus infinity, this is going towards minus infinity. So at this point, you have to introduce a new concept, which is you know, side limits, directional limits, left limits. I don't know if you've ever had any of those, but we can just say one side. Let's just say lateral limits. Okay. What does this mean? It means that we're just going to take the limit and then the limit when x goes to 1 from the positive side. So basically the limit when I go to 1 from this side, this is going to be limit when x goes to 1 with a positive. And this here is going to be limit when I go to x1 with a negative. Okay? Same thing, limit f of x and limit x1 minus f of x. Okay? And the condition for the function to be continuous at that point, I need to have all these limits being equal. So I need to have limit of f of x1 plus f of x is equal to limit x1 minus f of x is equal to f of 1. That is a condition for it to be continuous. Okay, and in this case, now let's just see how we can compute them. So I have I have limit when x goes to 1 with a plus. So again, I'm looking at this limit. I'm only looking at this side. I do not care about this for now. So limit when x when 1 with a plus, f of x, which is the same as limit when x goes to 1 with a plus of 1 x minus 1. Now, x goes to 1 with a plus, it goes to 1 from the positive side, but it still goes to 1. So what does this go to? It just goes to 0, right? 1 minus 1, it just goes to 0. The only difference is that it goes to 0 with a plus. And remember, this is one of the limits that I showed yesterday, and I told you guys that you got to understand. Any constant over 0 goes to infinity. The only difference is that if this is positive, it will go to plus infinity. Everyone follow on that? Okay. Now, the opposite limit when x goes to 1 with a minus, f of x, just 1 x minus 1. And now kind of the same logic appears. This still goes to 0, but it's just from the negative side. So instead of being 0.0001, it's minus 0.0001. So this just becomes minus infinity. Okay? Obviously, in this case, you know, these limits are not equal. So there's no chance that this is continuous. Okay? So not continuous. From this, not continuous. Okay. Any questions on this? Or was it that it kind of makes sense a little bit? Okay. So now we're going to do some sort of example that you will have at some point in your seminars, and I think it's better to do it with me, and maybe, you know, I'll do the easy example because you guys are better than me, and you guys are going to do the hard example during the seminar. But there are functions that just sound like this. I of y is equal to y for if, let's just put some numbers. If y is smaller than than 2, and 1 minus t times y if y is greater or equal to 2. right? This is a function. Is it well defined? Sure, makes sense. I mean, I can any value y you put in here, I can output a value for you, so it works out. It's a well-defined function. Now, bottom rule for this class: any function that looks polynomial, like you see powers, multiplication, addition inside, that looks somewhat okay, like as a formula, and not like this with square brackets, you can kind of automatically assume that it's continuous. You don't need to prove it. But when you see square brackets and the fact that it's defined on intervals, you need to show that it's continuous at that point. Okay. So what am I going to say right now? I'm going to say that I of y is continuous. I would say you don't need to prove it unless you're actually specified that I of y is continuous for everything outside of 2. Okay, 2 is the problem. I just don't know if it's continuous at 2. I don't know how this function looks. So I of y is continuous everywhere but at 2. So now I just gotta see if it's continuous at 2 or not. Okay, how am I going to do that? Whenever you see this type of problem with defined on multiple, I don't even know what to call them, multiple, I guess, intervals, you always got to do the lateral thing. So I'm going to take limit when y goes to 2 from the positive side of I of y, and limit when I goes to 2 from the negative side, I of y. Okay, so again, when you're asked to prove continuous at a point, this is standard procedure, unless you want to actually use the delta, epsilon, whatever definition, which I highly do not recommend. This is, I think, the approach. So I'm just going to consider these 2 lateral limits, and if I prove that they're equal, I'm done. It's continuous. If I don't prove that they're equal, it's not continuous there, and I'm done anyway. Okay? Now, if it goes from 2 with a plus, so just so we have a graph, so we know so you guys can follow me. If this is 2, everything for y positive, so for y greater than 2, is going to be 1 minus 2 minus t y. Okay, the function takes this value for any y greater than 2, and takes this value for any y smaller than 2. Okay, that's what the definition says. So in my case, when I'm coming from the positive side, this is just limit when y goes to 2 of 1 minus t times y. Yeah, I wrote it correctly. Okay. And when it comes from the negative side, it's just y. Okay, do you guys see the difference? Since this function is defined on intervals, when I'm coming from the right-hand side, I have to take one value of the interval. When I'm coming from the left-hand side, I got to take the other value of the interval of the function. Okay, that's the whole idea when you have functions defined like this, and you're trying to compute lateral limits. So now, let's not overthink it. Y goes to 2, t is a constant, so this is just 1 minus t times 2. This is just 2. And now, in order for them to be continuous, I just have to make these equal. So, I is continuous at 2 if and only if t is equal to 0. And I'm done. Okay? Now, I think that kind of solves a lot of the parts. Yeah. Yeah.
Can you draw the left in your row, and is that the notation for if and only if?
Yeah, this is if and only if.
Okay.
It's I can
Like that. Okay.
Double-sided arrow. This is if and only if. You can write it in words, it just refits, I guess. But this is if and only if. Sure. Okay, now, I don't think you're ever gonna get something like show that f of x equals 2x is continuous. You're never gonna have to show this, okay? I've never seen this as a requirement in this course. Now, if you want to show this, the way you can either use the definition, which you would just say, okay, it's continuous if limit when you have x going to a of f of x is equal to f of a. And then you just have to use the alpha delta, which I'm not going to bother with. Or you can just say, okay, limit f of x going to a is still, it still limits x going to a of 2x, which is just 2a, which is just f of a by definition, okay? So that's why I'm saying that it's, if they ask you to prove that a function is continuous and it looks nice, like 2x or some x to some power or something, then there's not actually anything to prove. You just got to write the definition. But I don't think that's going to happen. So I'm just, that's just there. Now, let's just take some examples. So I think it's a good, I'll just write these examples and I'll give you, I mean, there are 4 of them. I'll give you 5 minutes for them. There are 4 examples, 5 minutes. I mean, that's more than enough. And then we're going to talk about them together. And then, yeah, and then we're almost done. So these examples look like this. 0 with a minus. This is a very tricky one. Just a disclaimer, none of these things require you to do any heavy math or anything. It's literally just 2 expressions to the right, the solution, including the solution. So don't overthink it. Okay. I've received some weird, not some weird question, but I guess surprising question. This notation, absolute value, when you have absolute value of a, I'm not gonna, let's just put numbers, okay? Absolute value of any positive number, so of 10, absolute value of 10 is equal to 10, and the idea that absolute value of minus 10 is still equal to 10. So basically, absolute value just transforms negative into positive, and positive leaves them the same. Okay, it's just absolute value. Anyway, yeah, let's just take 5 minutes, 10:50, and then I'll write them out and go for them. Okay. I think 5 minutes are more or less over. So where are we at? Did we do all 4 of them? Everyone confident? Makes sense? Hopefully. I don't know. Let's see. So what's happening here? Who said this limit is gonna be infinity? The first one. Hands up. Who said it's gonna be 0? Hands up. Okay, so I see we had some little problems here. Okay, let's see where we're at. So what's the problem here? The problem is the following, that if I just automatically just plug in, like always the idea when you're doing a limit is assess the limit, okay? So the first idea is just to plug in the limit. Maybe it just works out. Maybe it's just one of the obvious limits that I gave to you in the start, one of the 4s. 4, remember constant over infinity and constant over zeros. If it's one of those 4s, you're done. You don't need to do anything. It's over immediately. The problem in this case is that if I plug in, I get 0 minus 0, again, 0 minus 0 over 0, which is going to give me 0 over 0, which in limits is what is called an undetermined case. 0 over 0 and infinity over infinity, you need to give me an extra argument. You need to convince me that the limit is what you say. Okay, and that was my example yesterday when I gave that x plus 1 over x plus 2 or something like that. It was quite obvious. I agree it's 1. But you always need to have an argument when it's infinity over infinity and 0 over 0. Okay? In this case, you technically might not even be able to solve it if I didn't write it with absolute value. Why is that? What did I say is absolute value of a negative number? It's just minus itself, right? Like absolute value of minus 10 is equal to minus 10, which is just plus 10, right? So if I just replace here, again, not changing anything, limit when x goes to 0 with a minus is x. This absolute value is, it's absolute value of a negative number, right? Because it comes to 0 from the negative, from the negative side. So absolute value of it is minus x. Minus x over x, right? This becomes plus. So this is just limit of 2x over x. Okay. Sure. So say that again. No, so absolute value. So this x is not an absolute value.
Yeah.
So it's just x. I haven't replaced anything. I'm just saying that, this is absolute value. I'm just replacing the absolute value. Absolute value of a negative number is minus itself. That's just how it works. But the idea is that I just get limit of x goes to 0 of this, which is just 2, because I can simplify the x out. So this limit is actually 2, surprisingly enough. Now, what's different in this case when limit goes to 0 with a plus? The absolute value of x is just the number itself. Absolute value of 2 is 2. Absolute value of 0.1 is 0.1. Okay? So this just becomes x minus x over x. Right? Which is just limit of 0 over x when x goes to 0 plus, which is just 0. Now, small argument to be had here. You could ask me, okay, this is 0, but x also goes to 0. Why is that function 0? Was that what you're going to say? Oh, sorry. Okay. And the argument here is that this is 0, like 0.000000, completely 0. When x goes to 0, it will never reach 0, but it's going to be 0.0001 at some point. So that's why it's good to remember limit of 0 over x is 0. Okay? Because 0 is just 0. This x is never going to reach 0. It's just going to be 0.01. Now, let's just see here. What's the idea here? Limit when x goes to 5 with a plus. If you didn't get my arguments here, I would highly, I assume not this session because it's, it's all with the submission and everything. But next week, I would highly advise you to look over them, and you haven't understood what I'm saying in these four, I would say, pretty simple examples, then just ask me in the session or something, because these are what I'm doing here is, you know, it's kind of the starting for what's going to happen in big limits. But when x goes to 5 with a plus, I can just replace this x here with 5. And if I replace it down below, I'm going to get 5 minus 5, 0. But the idea is that I get 0 with a plus sign, so it's a positive number. So it's 0.00001. Okay? So this becomes infinity. And when I go to the other side, I do the same exact thing. The only difference is that this becomes 0.001 with a minus in front. So this is minus infinity. Okay. Now, before we go on a break right now, in which, you know, you can think about these and ask me after the break, I think we have an announcement. Yeah, we have an announcement about student council, if I understood correctly. Yeah, I have no idea.
Hei, jeg er Fredrik. Den linjeforeningen har.
Okay, guys. So, let's do some clarifications here. So I got some questions in the break, and I just wanted to make sure we're all on the same page. If this is 5, and I'm saying x is going to 5 with a minus, I'm basically saying that all x's are here, and they're just getting closer to 5 on this side. So all x's are of type 4.999999, okay? When I'm saying x is going to 5 with a plus, I'm basically saying, you know, this is 5, let's make it bigger. I'm just saying that x is going to 5 from the right-hand side. So we're just getting closer to this 5. So it's of type 5.00, 5.001, okay? Just so we're clear on that, what it means when I'm going x to 5 with a minus and 5 with a plus, just so we're clear on that. Now, coming back to these limits, I got some pretty good questions. One of them was, why is there a 5 up top and a 5.001 and 0.01 up top below? And I fully agree. If I were far, I should have just written this is actually 5.0001. I just replaced with 5.0001, showing that it goes from the right-hand side. And here, since it goes to the left-hand side, I just have 4.999999. Okay. Now, another thing that I got asked something like, is this a fair response for an exam or something like that? And I'm gonna answer it this way. In an exam, everything that I'm doing right now, I'm basically just replacing with this 5.001 or 4.999. I'm just doing that to show you how I'm thinking and show you how you should be thinking and replacing. On an exam, this is something that would go on your cheat sheet. You don't need to show me this limit is equal to minus infinity. This, you just write minus infinity. I'll be like, okay, sure, makes sense. Okay. The only other sense that I can see for this, outside of going on your head or your scrap paper, is in the seminar. If you just want to write it, just so you don't want to explain to me why you said some limit is something. Okay. But in an exam, this limit, and particularly any limit that is of type 0 over constant, or constant over 0, or something like that, and it's pretty straightforward, like I don't have to do 10 pages of math to see that's that case, you can automatically say the answer to it. Okay. So in this case, what was it? It was just a constant over 0. Okay. Like, you don't need to prove me that that is infinity. I understand that. It makes sense to me. The only cases in this class that you need to treat very respectfully is plus minus infinity over plus minus infinity and plus minus 0 over plus minus 0. This is just a way of phrasing that when you have a fraction where the numerator goes to infinity and the denominator goes to infinity, or, or 0. In these, I guess 2, but you can argue that they're more, whatever, with plus and minuses. In these 2 cases, any argument except for one particular case, which I'm going to show you at the end of the lecture, any argument you give me in words, I will probably decline it. Okay? Because I can make these limits of this type go to literally any number in the world you want. I can make infinity over infinity go to 0 minus infinity, 5 or 47.2. Okay? So that's why you got to be very careful with these. Very, very careful. Now, you're lucky that for these cases, you have a theorem that just makes things easy instantly. So there's actually a theorem for this, and it's called L'Hopital. This is whenever you don't have a trivial limit, such as constant over 0, constant over infinity, or something like that, you will use L'Hopital. This is your only tool of solving stuff. Okay, literally the only thing you know, and when solving limits. And what does it say? It says, well, if you have f g, I guess this is L'Hopital extended, but I never knew that before, so I'm not going to force you to know. But if you have f and g, 2 functions, in these cases, in one of these cases, then you can just, and you have to compute limit x going to a f of x over g of x. And this is the case, for example, if f of a goes to infinity and g of a goes to infinity. So if you find a case where, I don't know, I'm going to write here, example, f of a goes to infinity and g of a goes to minus infinity. I don't know, if you just plug in a here, you're not going to be able to solve it because you're going to guess infinity over infinity or infinity minus infinity over minus infinity. In this case, you have to use L'Hopital. And this is equal to the limit when x goes to a, f prime of x over g prime of x. Well, this is all L'Hopital says. And this is everything you need. Okay. Now, questions that I've received over the years. Can you use L'Hopital multiple times? Yes, you can use it 20 times if you are in the condition. So what do I mean by that? If I see that my f of a goes to infinity and my g of a goes to infinity, I don't know, I apply L'Hopital, okay? And I get this new function, f prime of x, g prime of x. If in this case, f prime of a still goes to infinity and g prime of a still goes to infinity, I can apply it again and again and again until you get the answer. So you're like, I don't know if you guys are following, your whole idea of solving problems in this class, limit, is I evaluate the limit, I see if it's one of the trivial cases, constant over infinity, constant over 0. Usually it's not going to be. You're going to end up in one of these cases, infinity over infinity or 0 over 0, in which case you apply L'Hopital. You apply L'Hopital, and then you see, am I in a better case? Am I in a bad case? If you're in the same case or in a bad case, you just apply it again until you reach one of the trivial limits. Let me show you an example. I just have limit when x goes to, let's do this. X goes to 0, e of x minus 1 over x. I cannot emphasize enough. The first step is always evaluate your limit. Do not apply L'Hopital if your limit is not one of these cases, because it's wrong and you're going to lose literally everything at that point. If the limit is a trivial limit, so it's not one of these cases, and you apply L'Hopital to it, you will literally get 0 out of 10 or maybe 1 out of 10 for pity. Because you're basically showing that you cannot evaluate a limit and you don't know L'Hopital. Yes?
But is the result wrong or is it just the bad method?
It's both. It's all of the above. It's all that you could have missed on the problem, you missed. Okay, now in this case, first step, evaluate the limit, which means just plug in and see what it is. I plug in 0 and I see this is 0, so this is 1, 1 minus 1, this is 0. Again, I'll do it again, I guess lower. X goes to 0, I plug in x here. I get e to the power of 0, which is 1. 1 minus 1 gives me 0. X goes to 0, so this is 0. Now, I don't need you to, whenever you apply L'Hopital, I don't need you to write L'Hopital. Only thing I need you to show me is this is a 0 over 0 case. So basically showing me, yo, dude, I just analyzed this and I got that it's one of the cases for L'Hopital. So just write 0 over 0 or infinity over infinity, whatever the case is, and then just say LH. That's enough for me. I don't need anything else. Okay, then you can apply it. So this is just equal to limit 0, and now I take derivative. Okay, derivative of x with respect to x is just 1. Fair? Derivative of e to the x is just e to the x. Derivative of 1 is just 0. So it's just this. Okay? Now what is this? Limit x goes to 0, e to the x. Again, evaluate. Okay, I could have given a more complicated example, I guess. But x goes to 0, 0 here, e to the 0, 1. My limit is 1. Okay? Any questions on this? Okay, let's see. Let's try another one. Let's try another one. Limit when c goes to 1. Maybe this is a little bit too hard. Let's not do that. Actually. Okay, let's take something else. Limit when x goes to 0. X goes to infinity, let's say, e to the x minus 5x plus 2 over 47x squared minus 25.2. Okay? First step. First step is we evaluate, always evaluate. Like, whenever you're doing a function, every step you do, you have to evaluate, see if you're in the right condition. So I'm evaluating right now. X goes to infinity. Boom. Let's put plus here because it's easier for you guys for now. X goes to infinity. E to the x. E to something very big. This goes to infinity. Plus 5x. This goes to infinity. Plus 2. I mean, infinity plus 2 is still infinity, right? We learned that from the cartoons. Okay, so my denominator is infinity. Everyone follow that? Sure. Now let's look down below. X goes to infinity. X squared goes to infinity. 47, doesn't matter. 20 minus 25.2 doesn't matter. So this is still infinite. That's an 8. This is still infinite. It is not 8. Okay, now I'm in an infinity over infinity case. As I told you, you do not have a lot of techniques on your hand. So just take advantage of the one you have. It's infinity over infinity case. I don't know what to do anything else for now. Or, you know, there are some computational tricks which they're on the seminars, and I'll probably show them during the seminars while you're doing the exercises. But this is all the theory you have. Everything else is more some computational trick, which is only gonna make things shorter, but you can always use L'Hopital basically. So I have an infinity over infinity case, so I'm gonna apply L'Hopital, and I get limit x goes to infinity, e to the, again, derivative of what's up top. E to the x derivative, e to the x. Plus 5x derivative, 5. 2 goes away. 47x squared, that's 47 times 2x. Minus 25.2 goes away. So I'm stuck with this. Now, what do we do with this? Again, evaluate. X goes to infinity, this goes to infinity, infinity plus 5, that's infinity. 47 times 2, I don't care. X goes to infinity, it's infinity. Okay, so I have, again, infinity over infinity. What do? We just apply L'Hopital again. So this is infinity over infinity. I'm just going to apply L'Hopital. Now I just get limit. X goes to infinity. E to the x stays the same. And this is just 47.2. Now, same thing. I evaluate again. X goes to infinity. This is infinity. This is just a number. So this is just one of the trivial limits that I gave you yesterday, right? One of the 4, infinity over a constant, which is just going to be infinity. So I think this is a great example of what I'm saying. You start with something that looks ugly, and then you evaluate it. If it looks ugly, it's usually one of the cases of infinity over infinity or 0 over 0. Otherwise, it wouldn't look ugly. And I apply L'Hopital. Then I evaluate again. If I'm at one of the basic limits, I'm done. If not, I apply L'Hopital again. So I apply L'Hopital again. I get to one of the basics, which is infinity over a constant. I write infinity. I'm done. I move to the next problem. Okay. Any questions on this? Yeah.
Do you always find the derivative separately?
Yes. Yes. That's no. It's not a quotient rule. It's not something like that. Where do I write L'Hopital? I actually wrote. I am terrible with notes. I wrote L'Hopital. I think I wrote L'Hopital specifically like that. Anyway, I'll write it again because apparently moving on. Yeah, I wrote L'Hopital like this. So I said, if you're in one of the cases, limit when x goes to a of f of x over g of x is equal to limit x of a f prime x g prime x. I wrote it like this. I'm going to write it capital, not fx gx everything prime. So I don't take a derivative of the quotient rule. I take a derivative of the denominator and or what's up top and what's below, separate all the time. Good question. Anything else? Cool. It seems pretty obvious then to everyone. There's one very, very important limit that I think you're actually going to have to prove in the general case. I kind of gave you the idea here how to prove it in one of the seminars, but I told you that whenever you have infinity over infinity or 0 over 0, whatever, you have to apply L'Hopital. There's one case in this class, and literally one case, which is just limit when x goes to infinity of e to the x over x to a. Yeah. Where a is a number, any number. Okay? This is the type of limit that it is. And what is this? What this limit is basically saying that exponential grows faster than any power you can give me. That is what this thing says. Exponential is much, much bigger than any number you can give, any power you can give me. Okay? And you probably, by the exercises we did right now, I kind of tried to show you the idea. Right? I took an exponential here over x squared. In the previous example, I took exponential over x, and I showed that it all goes to infinity. What is the idea? Just think about it. If I just apply L'Hopital, whatever power you give me down here, I could just choose 1 million. Whatever power you give me down there, I'm going to keep applying L'Hopital over and over and over again. The idea is that this exponential will never go away, as you see, because derivative of e to the power of x is still e to the power of x. So I can apply L'Hopital as many times as you want. This E is not going away, but the power is dropping. I go from x to the power of 2 to x to the power of 1 to x to the power of 0. So that's the idea. That's the proof. And the idea is, I don't know, just graph, just go and play, I guess, on, there have to be so many graphing options. Just try to graph e to the x and x to 100,000, okay? If you just scroll the bar enough to the right, you're gonna see that the exponential at some point just explodes, okay? That's the idea. And this you can use in an exam everywhere without proof, basically just saying exponential grows faster than power, or I've just seen exponential greater power. I don't know, any notation, anything works. I know what you're talking about, okay? Especially if the limit looks like that. Might be a trivial question for you guys, but if I have limit when x goes to infinity of x to the power of a e to the x, what is this? So I'm basically just flipping the limit from above. What is this? Yeah, exactly. Yeah, it's just 0. Because, you know, it's either 1 over infinity, you know, this is in quotation marks, right? It's 1 over infinity, or use the same argument, exponential just grows much faster than power. So at some point, this is going to be way bigger than this. So that's why this is 0. But again, exponential grows faster than power. This is your main argument. Outside of this exercise. Now, I guess I'll just do at the end because there's no application in this class. I'll just give you guys definition of what a sequence is, a convergent sequence. I don't know if we're going to use it, but these cases, the infinity over infinity and 0 over 0 cases are called indeterminate cases. Because without proof, you can't argue with me. I will deny all your arguments unless you give me solid proof that a limit of that type converges to something. Okay? Now, what happens if you're given a limit that you get? Okay, let's try. Are there any other indeterminate cases? Are there any other things that you have questions about? Any other limits? Let's think about it. If I have infinity times a constant, you know, let's say the constant is positive. If I have infinity times a constant, what's this? If I multiply infinity a couple of times, positive. I mean, I just have multiple infinities, so infinity, right? Infinity plus constants, any constant is still infinity. 0 times a constant is still 0. Again, I'm assuming positive. Obviously, if it's negative, this changes to plus minus, but you know, I'm just assuming positive. Now let me ask you a smart question. What is infinity times infinity? Yeah, exactly. It's just much bigger. That wasn't the smart question. The smart question is, what is infinity times 0? No. Okay. So let me rephrase. So I need to change something like this. I need to change it. Let's say so infinity times 0, like actual number 0. So if I have limit of when x goes to infinity of x times 0, like literal 0, not something that converges to 0, literal 0. This is 0. I agree with you guys. But if I have infinity times, I'll write it in words, something that converges to 0. Okay, what is this limit? That is the smart question. I mean, do you want to think a bit about it a little bit? I'm gonna say partially right. Partially right. The answer is this is again an indeterminate case, and that's why I said partially right, because a limit of that type can converge to any number. So I can't say you're wrong because it can converge to that, but it can also converge to 5. So here's the idea. We're gonna do an example. Whenever you have infinity times, again, something that converges to 0, it's indeterminate case. And now we're completely messed up. We're stuck, right? We can't do anything. We don't know how to address these cases because the only method I told you to address this indeterminate cases is L'Hopital, right? So let's take an example and see how we deal with it. Let's just say limit when my head hurts. When x goes to infinity of this is actually kind of bad. ln of x times e to 1 minus x, something like that. I need to think of a smart example, really. But because in this case, you can just flip it. But whenever you have, let's evaluate this. This is just infinity. ln of infinity becomes infinity. E to the minus infinity, this just goes to 0. So I have infinity times 0 case, okay, which is kind of bad. I don't know what to do with it. So I'm telling you again, the only method you know and how to deal with indeterminate cases is L'Hopital. So what is your logic right now? Because my logic is, okay, let's make this thing in a L'Hopital form. That should be going through your head. Whenever you find a multiplication that's indeterminate case, you have to get into a fraction form. So the way I'm thinking is for any number in the world, z is equal to 1 over z. Everyone kind of on board with that? So z times 1 over z, and this is a trick that you're actually gonna need, and it's quite spread out in this class. Okay, let's take it step by step. Does everyone agree with the second thing I wrote? Now I'm just gonna move this to the other side. So I'm dividing by 1 over z. So I just get z is equal to 1 times 1 over z. Okay, this is a very, very cool trick. Does it make sense to everyone? So I'm just flipping it. That's the whole idea. I'm creating my fraction. So when I have this limit of x goes to infinity, ln of x times e1 minus x, I can just write it as limit when x goes to infinity, ln of x times 1 over e1 minus x. Okay, everyone kind of understood. So this thing that I'm doing right here is just to get me in an indeterminate L'Hopital case because I'm stuck. When I get infinity times 0, you're in this class, you don't know any theorems or anything that is going to help you solve the problem. So you need to go back to L'Hopital. That's why my idea was like, okay, I have this product, let's make it into a fraction. Because let's see, I just get limit when x goes to infinity, ln of x 1 e1 minus x. Okay. Now, Ask me that again. I think my brain stopped.
Over e to the power of minus one minus x brackets with one minus x brackets, right? It is, yeah.
I can. I'm so bad. Oh yeah, sure. That's the next step. That's why I was not quite happy with this example because it's kind of obvious and it works out very nicely. But again, I'm doing the easy things. You're doing the hard parts. So now again, before doing that change, so let's evaluate this because in some cases you're not going to be able to flip it nicely. So unfortunately, but let's evaluate it. Okay, let's evaluate what's up top. When x goes to infinity, ln of x goes to infinity. Okay, we're all on board with that. Now let's see what's down below. When this goes to infinity, this goes to 0. 1 over 0 goes to infinity. Okay, so as we see right now that this product here was just this infinity over infinity thing in disguise for us. That is the idea. Now, I can immediately apply L'Hopital to it. I agree with you guys. Immediately apply L'Hopital to it. But it's better, just as I recommended on the Lagrangian, before you just go into the hard computation, just spend a second to see if you can just make it nicer. Because I don't know what you guys know, but taking derivatives of fractions kind of sucks. It's kind of hard. And you get a lot of terms and it kind of complicates a lot. So I hate doing that. That's why, as they're saying, I can just write 1 e1 minus x. I can just write this as e to flipping this, x minus 1. Okay? Or I think the way you said it is e to the minus 1 minus x. I think is that what you said, I think? Yeah. Okay. So my limit is actually limit when x goes to infinity of ln x over e x minus 1. And this is a very nice function. Like I can apply L'Hopital to this all day long. Okay. So this is infinity over infinity. I apply L'Hopital to it, and I get limit x goes to infinity. What is the derivative of this? 1 over x. What is the derivative of this? It's just ex minus 1. Okay. Now I evaluate this again. If x goes to infinity, this goes to infinity, 1 over infinity, this goes to 0, this goes to infinity, this goes to infinity, not 0. Okay, so I get 0 over infinity, which is just 0. Okay, looks pretty good, I think. Any particular questions for this one? Okay, then if you guys are so confident, let's just do an example. But you are solving it this time. Limit when x goes to 0. What was it I found? X ln of x. This looks nice. Okay. You have 2 minutes. 2 minutes, I think, is more than enough for this limit. Okay, how are we? Did everyone finish? Very good. Okay, so I don't need to solve it anymore. You guys are good on this? Or? Okay, what answer did we get? Did we get infinity? Zeros everywhere? And one? So let's see where we're at. Let's evaluate this first of all. Maybe it's so easy that I did a mistake and it just equals to something. When x goes to 0, this goes to 0. X goes to 0. When x goes to 0, this is here 0. But what is ln of 0? Minus infinity. So I have 0 times minus infinity. Not too hot. I can't solve it. I don't know what it is. And so it's an indeterminate case, so I need to use the trick. And what I'm going to use is exactly the same trick I used above. I'm just going to say x times 1 over x is equal to 1. So x is just equal to 1 over 1 over x. So I can just write limit x goes to 0 of 1 over 1 over x ln of x. So this is just limit when x goes to 0 ln of x 1 over x. Okay, cool. Now let's evaluate this. X goes to 0. This goes to 0. 1 over 0 is infinity. And the same argument here is that this is minus infinity from above. Same argument. So I have infinity minus infinity over infinity. Indeterminate case. So I'm still stuck. What's the difference? I have a fraction, so I can apply L'Hopital. That's the difference. I have a way out. So I'm just going to do that right now. I just get limit when x goes to 0. Let's just assume x is positive for simplicity, but we'll get to that some other time. 1 over x over, what is the derivative of 1 minus x? 1 over x is just minus 1 over x squared. Cool. So now, before I evaluate, that's why I say always evaluate and take a little bit of your time, because if I evaluate now, where am I at? I have 0, 1 over 0, this is infinity. This is 0. So this is minus infinity. So you would be like, okay, this hasn't worked. I got to apply L'Hopital again and again and again. And I promise if you go on that road in this problem, you're never going to solve it. You're never going to end up actually solving it. You're just going to keep going. So that's why I said before, evaluate and also try to make it look more compact. So in this case, there's 1 over x here, 1 over x squared here. So why not just make it look nicer? So I'm just going to multiply the whole fraction by x squared. Just some fraction operations. So I get limit when x goes to 0, x squared times 1 over x squared times minus 1 over x squared. Bam, this goes away, and I get limit when x goes to 0 of x over minus 1. This goes to 0, so this is just 0. Right, x goes to 0, and that's just a constant. Now, it's 0, it's assumed that 0 plus and minus, you don't have, on the solution, you don't have to write, there's no such thing as plus 0 or minus 0, it's just 0, okay? But yeah, this was the problem. Pretty straightforward, I think. And starting next week, I think you should be able to do these, and probably even more complicated than these. Right? We all believe in this. Okay. Now, there's one thing that I have to introduce to you guys, but I'm not good. I don't think we ever used this, but we're just gonna do it. It's limits of a sequence. And we're gonna do an example of this, and we're probably gonna end it. So I'm saying that x1, x2, xn, and it keeps going, converges to X star. Again, formal definition, if for any epsilon greater than 0, there exists an n such that X star minus Xn smaller than epsilon for all n. Okay. Now, let me explain this. Before you panic. This is like the formal definition. Before you panic, let me explain it. I just have the sequence of number. I just have like an infinite line of numbers. You just choose the numbers. When I'm saying that they converge to a point, I'm saying that after number 1 million, they are all very close to this point. Now let's take an example. Let's just take the sequence x1 is equal to 1 over 1, x2 is equal to 1 over 2, x3 1 over 3. I think you get the idea. Xn is equal to 1 over n. Right? People say, or I don't know, I believe so. Hopefully you will after I show you that this sequence converges to 0. Okay? People say that this sequence converges to 0. So by definition, after some point, let's say after x 1000, which is 1 over 1000, all points following are close to 0 as close as I want them to be. And the way you prove this is just, if you were to do sequence, I would just say, okay, you give me, this is how you would prove, this is like informal for those of you interested in doing math. And then I'll show you how you do it in math 2 here. But the way you prove it is you give me how close the numbers, the numbers you want. You give me how close the numbers you want to be to 0, and I will give you n after which you can take them all. After which all are close. Again, if you're not interested in doing math, you don't really need to focus on this necessarily. But it's here, so I have to more or less guide you through it. So for example, if I want all my numbers here to be close to 0 in the vicinity, or as close to them as 0.00001, I will just choose all the numbers after x 1 million, which is going to be 1.1001 million, 0.01. That's the idea. I'm just going to take all the numbers after x 1 million. So take x 1 million 1, 1 million 2, etc. Now, how do you prove it in math 2? You're just going to say, yeah, it's simple, because limit of 1 over x when x goes to infinity is 0. 1 over infinity 0. This is how you do it in math 2. This is how you would prove sequences if you're planning to do math. So if you're planning actually to do math, talk to me and I'll get more in detail. Otherwise, this is enough for math 2 only, and economics, I think, in general. I think we're ending with 6 minutes early. That's fine by me. If you have any questions, let me know. Yeah.
You show the formal definition.
Oh, yeah, sure. I don't know why I did that. Yeah, sorry. Sorry about that. This means exists. Sorry about that. Yeah.
On the lesson time, I think I can see the reading to the next couple of weeks from tablets or.
Great question. I thought they're gonna be just posted from last year. I'll talk to who's in charge, I guess, to post them. But if you guys have access to last year's, not Canvas, but schedule, right? Just, they should be there. Next semester, or next week, we're just doing, start of integrals. That's what we're just starting. But I think the section should be there on previous plan. If not, just let me know. Cool, then have a great day.